Hey guys, welcome back. In this video we are calculating the elastic strain energy for a simply supported beam with a point load. In this video we're just going to be talking about the strain energy that's associated with the normal stresses due to bending. We're going to ignore the effects of shear for this example. But with that said, let's go ahead and work our way through this problem. We're basically going to have to find the strain energy that's built up on the left side of the point load and then also on the right side, add those together, and we're going to find the total strain energy. So let's get started here. Let's draw our free body diagram. Let's put on 90 kilonewtons going down, and our A here is just going to be, well, we'll take the ratio. This is going to be 0.8 over 1.2. 1.2 is the length of the whole beam times 90, and that's going to give us 60 kilonewtons. That is our A, and then for our B, we can do the same thing. We'll just take the other side. We have the ratio that's 0.4 over 1.2 times 90. That gives us 30 kilonewtons, and that is our B. Cool. So the other thing that we want to do now is we want to look at the moment. You could even draw a little bit of a moment diagram, bending moment diagram as we go across the beam. We can just draw our bending moment diagram like this. And this is a pretty simple problem. Let's write that a little bit nicer. The bending moment diagram is basically just going to look something like this, where it's going to peak out at that point load. And we're going to be talking about the left-hand side as section 1, like that, and the left-hand side as left-hand side as section 1, and the right-hand side as section 2. What I would like to do for this problem is we'll take we'll say when we start at the left-hand side and go right, we'll call that x1, and if we start at the right-hand side and go left, I don't know if I said that right. Left-hand side going right and right-hand side going left, we're going to be referring to this distance traveled as x2. So when we look at the moment in section 1, maybe let's write it up here. When we look at the moment in section 1, this is going to be equal to, basically the shear here is going to be 60 kilonewtons, so we have this as just the moment as we travel along will be 60 times x1. And then in the region 2 here, moment 2, basically we're just going to be having 30 times x2. That's the moment as we go this way from the right hand side. So if we look at it from either side, then the moment here at that peak is just going to be equal to 24 kilonewton meters. Alright, cool. And we can look at that from 60 times 0.4 or 30 times 0.8. That's going to give us the same thing. But we're actually not going to need this number. That's just pointing that out. Okay, so what we're really interested in is the strain energy. So we'll just come down here a little bit. Maybe we'll change back to black. We're looking for the total strain energy. And so this is going to be equal to the strain energy in section 1, which is to the left of the point load, plus the strain energy in section 2, which is the area to the right of that point load. So if we want to write out the expression for this, well, for the strain energy in region 1, again, we're looking at the normal stresses due to bending only, so we can have this expression here where we say we go from 0 to 0.4 meters, right? That's this distance right here. And the expression from the previous videos for bending is we're going to have m1 squared over 2ei. And this is with the dx1. We're dealing with this distance traveled here. Okay, so that is the strain energy in region 1. The strain energy in region 2 is we're going from this side that way. It's just easier to integrate it going that way. So we have from 0 to 0.8 for m2 squared over ei, and this is dx2. Cool. And if we integrate both of those, we're going to find the total, basically the area under here, add them together, and we're going to find the total strain energy. I'll just point out right now that the expression here, m1 squared, well, we can even just draw the arrows right here. m1 squared is, now let's do it like this. This is equal to 60 squared times x1 squared. And m2 squared is equal to 30 squared times x2 squared. All right, so keeping that in mind, let's pull out the constants from this. So here we can bring out all the constants. So we're going to have the 60 squared is actually a constant. So we have 60 squared, and maybe we should actually start putting in some units here. So this is 60 kilonewtons, right? Because that's kilonewtons times meters. So 60 kilonewtons all squared. And then this stuff on the bottom is 2ei times that integral from 0 to 0.4. And what's left here is x1 squared with the dx1. Alright, now for this section, for the strain energy in region 2, we can pull out the constants again. Alright, so we can perform the integration here. Pretty simple. Alright, so let's expand this out, but first we need to figure out what E and I are. E is 200 gigapascals, and I is 3.33 times 10 to the 6 meters fourth, based on this cross-sectional area of the beam. Alright, so let's bring that down. So if we look at this, actually we can combine these because this denominator is 6ei, and this one is also 6ei, so let's put everything over 6ei. Alright, let's cross out some units here. We're looking for newtons times meters for our final answer. We have meters squared here with meters 4, so we're going to bring that down to a 2. Because we're adding newton meters plus newton meters, this whole thing is just basically like a single term of newton meters. So we can take these 2 meters out of the bottom and reduce that down to 1. But when we do this, be careful. We're don't not cube. This is 0.4, so we got to keep that cube in there. And don't not cube. This is 0.8, so we got to keep that in there. And then we can cross out newtons again. That's just going to become 1. But again, don't not square the number like that. Alright, so what we're going to do is we're going to have 60,000 squared times 0.4 cubed plus 30,000 squared times 0.8 cubed divided by all this stuff, 6 times 200 times 10 to the 9 times 3.33 times 10 to the negative 6. This will be left, our final answer will be in Newton meters, and when you do put that in your calculator, it's going to spit out this number of 173 Newton meters. That's all that simplified. And Newton meters are joules, so this is the same thing as 173 joules. So there we go, we got our final answer here, 173 joules, and that is basically the total strain energy of this beam here once we have applied this point load of 90 kilonewtons 1/3 of the way across.